Question 4 here asks us about graphing using an activation energy. So it says thermite reactions are fast and very exothermic. They also have a very high activation energy of 145 kilojoule per mole. Graph the iron oxide thermite reaction with activation energy. So if I was to select my starting energy amount, and so I don't know what that might be. Let's say it's 500 kilojoules, just for argument's sake. The reactants have this energy, and we're going to have it be for iron 3 oxide solid plus 2 aluminum. And then the activation energy is going to go up to 645 kilojoules because it's 145 kilojoules more. And it's exothermic. And the difference in this is still going to be negative 851.5 kilojoules. My products were 2 iron solid plus aluminum oxide solid. And this value would be negative 851 less than this. So it'd be negative 351.5 kilojoules. This would be time. And we need, again, a title, something like enthalpy of thermite reaction for iron 3 oxide, something like that. That gets us through question 4. Question 5, though, asks us a question where we're using the reaction to heat some water. So it says 10 grams of copper 1 oxide was reacted with excess aluminum oxide and placed into a 5-liter tub at 21.0 degrees Celsius. What's the maximum temperature of water in this tub? Well, the number of moles of copper 1 oxide is related to the mass, which it said was 10.0 grams. Molar mass of copper 1 oxide is 143.1 gram per mole. So we can calculate the number of moles of copper 1 oxide, and it's going to be 10.0 gram divided by 143.1 gram per mole. And it's going to give us 0.0699 mole. And then that's the chemical amount, and the chemical amount times the molar enthalpy, which we've already calculated, will equal the energy transferred, which will also equal mc delta T. In this case, we want to calculate delta T. So it's going to be N delta H over mc. Now, the mass of the water is from the 5 liters, so that's 5.00 kilograms. And so I can take this 0.0699 mole times the molar enthalpy of the reaction for copper 1 oxide, which we calculated here was negative 390.0 kilojoule per mole. This is going to give me kilojoules in the reactants, and I'm going to divide by 5.00 kilograms, so my kilos will cancel out, and 4.19 joules per gram degree Celsius. My change in temperature is going to end up being, let's put that into a calculator, 0.06988 actually is what it was when I calculated its mass. I rounded off for you, so times 390. 390.0, and then divided by 5 and divided by 4.19, I get 1.3 degrees Celsius is the temperature change. Now, it's an exothermic reaction. You could use delta T equals T initial minus T final if it makes you happier to get to, but I know that the change in temperature is 1.3 degrees Celsius higher than it was initially. So my T final is going to be 21.0 degrees Celsius, the initial temperature, plus 1.3 degrees Celsius to give me a final temperature of 22.3 degrees Celsius from doing that thermite reaction in a 5-liter pail of water. Final question here is which chemical, copper 1 oxide or iron 3 oxide, is more thermally stable? Thermal stability is based on the formation enthalpy. So the more negative the formation enthalpy, the more stable. So the formation enthalpy for aluminum oxide is negative 1,675.7 kilojoules per mole, and the thermal stability, or the molar enthalpy of copper 2 oxide, we've already seen this, is negative 168.6 kilojoule per mole. And so since this is a much smaller or much more negative number, this is the more thermally stable. What that means is basically this chemical is going to take lots of energy to break apart. And if I wrote its formation enthalpy instead as a decomposition, so aluminum oxide breaks down into its components, I guess doing that, the enthalpy here would be, oh no, that's right, O2, so 3/2. Sorry, oh my goodness, terrible. My enthalpy here would be positive 1675.7 kilojoules. So essentially, it's going to take this much energy to break this down. So it's more stable because it takes more energy to break it down. And that can just be read directly off the formation enthalpy. The more negative the formation, the more energy it takes to actually break the compound down.